Okay, in this video I want to talk about when are we going to use a series to solve a differential equation and why. So if I look at this differential equation that's on the piece of paper right now, x squared plus 1, the quantity times y double prime plus xy prime minus y equals 0. This doesn't quite match the format of any of the problems we've looked at before. If I were to cover up the plus 1, then it would be Cauchy-Euler, but with the plus 1, it's not actually going to be Cauchy-Euler. It's not an x squared times y double prime and x times y prime and a constant times a y, because we also have this plus 1. So none of our existing methods really apply to this problem, and so maybe I can't find it using an explicit method.Maybe I can just find the series that represents the same solution. So with that in mind, that I'm thinking about using a series, let's think about, is this a ordinary point or a singular point? So we talked about in the last video that if you divide by the lead coefficient, we get y double prime plus x over x squared plus 1 y prime minus 1 over x squared plus 1 times y equals 0. And it's the only time that these two functions, our p and q, are undefined are when x is an imaginary number. So our only singular points are x is equal to plus or minus I. That's when the denominator would be 0. And so that means that x equals 0 is an ordinary point. And the reason this is important is that it turns out there's a theorem that says we can only find a series solution of the form y equals sum constants times x minus x naught to the n. We can only find a series solution of this form if x naught is an ordinary point. And so in this case, x equals 0 is an ordinary point, so we should be able to find a series solution of the form n equals 0 to infinity cn x minus 0 to the n, which would be x to the n. And I think I mentioned in the last video, but I'm going to say it again. Typically, we are going to be only interested in series centered at 0 because we don't really want to deal with x minus 5 to the n and having to plug in that a million times. So we're going to be mainly looking at, is 0 ordinary or singular? In this problem, it's ordinary, so we should be able to find a series solution of this form. In order to plug this into our differential equation, we're going to need to also know what is y prime and y double prime. So let's just go ahead and do that now. So our y prime, the derivative of a sum would just be the sum of the derivatives. Let's see, so I guess I'll write that step down, but I would probably skip this 100% of the time. And the derivative of a constant times the power of x is just going to be derivative of x to the n is n x to the n minus 1. Okay, and something we mentioned in class the last couple of days we were there in person is that when n equals 0, the first term is actually going to be c0 times x to the minus 1. But the fact that we have a 0 means that first term is just 0. So this series starting at 0 is going to be the same as the series which just starts at 1, since the first term of the top series is really just a 0. Okay, and then if we wanted to take y double prime, I could do the exact same thing again. I'm not going to run through the steps of taking the derivative of a sum. What's basically going to end up happening is we take the derivative of the power of x. So we'll end up with a sum cn times n minus 1 times x to the n minus 2. And again, we can play a funny game where when n is 1, this part is going to be a 0, and so the whole first term, the n equals 1 term, is going to be 0, and so this series doesn't actually start, whoa, badly drawn sigma. This series doesn't actually start until n equals 2, and then it would have the same inside. Cn times n minus 1 times x to the n minus 2. Okay. So this y, y prime, and y double prime are what I'm going to stick into the differential equation. I'll show those details in the next video.